All right, so in this video here, we're gonna give a brief introduction to some ideas that are quite topological in nature. And so for people that have taken analysis, these ideas should look familiar, but I'm gonna assume none of you have seen any of this before. And then we're gonna introduce the bare minimum of what we need to study complex analysis. All right, so the first idea we're going to discuss is the idea of open sets. So if you go back to calculus, we have these notions of open and closed intervals, right? And these are quite nice because we have a bunch of big theorems that depend on what these intervals look like. So the analogous for open and closed intervals are going to be open sets and closed sets here. So we're going to start off with a definition. So the first thing we're going to define is what is an open disk, right? So an open disk in the complex plane centered at point A and with radius r, and the notation we're going to use is going to be dAr, and this is going to be all the points in the complex plane, all right, so that Z belongs to C, and Z minus A modulus is less than R. All right, remember, so the modulus of Z minus A means the distance from Z to A, so we're looking for all points in the complex plane whose distance from point A is less than R. All right, so if I look at this here, let's say that's R. What I'm going to do is I'm going to look at all points here. So that's my A that are distance R or less than. Right, so again, I am using these dotted lines here to indicate that the points whose distance from A is equal to R are not included in this set here. Right, so that's what an open disk is. Right, so once we have that notion of an open disk, we're going to talk about what it means for a set to be open. Right, and a set is open if for every Z and S, so here's a definition, we can find some number epsilon, which is greater than 0, such that the disk Z, centered at Z, this point Z here, with radius epsilon, is contained in S. Another way of saying this is that this disk here is a subset of this set S. So a set is open if no matter what point I pick in that set there, I can find a disk around it of some radius so that that disk is completely contained in that set S there. All right, so that's the definition. Intuitively, what this means is that every point in the set is surrounded by other points in the set. So if you look at a point there, around it, it's going to have points in the same set itself. And in our language here, so really, even though we have not defined what it is, it cannot have boundary points, really. An open set cannot have points on the boundary. Right? And this, sometimes people say there's wiggle room or there's elbow room. So intuitively, that's, right, so each point has some elbow room. All right, so now that we have the definition, let's go ahead and look at a few examples. So the first example we are going to look at is the entire complex plane C. So the question is, if I look at the entire complex plane, so let's draw this here. If we want it to be open, what we need to happen is if I take any point in that set there, so no matter what point I take, I need to be able to find an open disk centered at that point there, so that that open disk is completely contained in our set S. Right? So that's the idea. And so, is this going to be open then? So if I take any point here, let's say randomly Z, can I find an open disk centered at that point there that is contained in C? Yes, right? No matter what open disk I take around this point here, it's always going to be contained in C. And the same thing for any other point here, right? So no matter where I take this point here, I can always find an open disk centered at that point contained in C. So this is open for the reason we just talked about. Since every point in C has an open disk centered at that point, contained completely in C. Right, so that's the complex plane here. So now let's look at the open disk DAR and see if it's an open set or not, right? So we called it an open disk here, so we would hope that it is an open set here. So I am gonna claim this is open, and we will save this for discussion in class. All right, so this will be one of the things I want you to look at. See if you can show that this is an open disk, and we'll talk about this in class. All right, so now that we have talked about open sets, we would like to discuss the idea of closed sets. All right, so just like open sets, these are quite important. So what we're going to do is we're going to relate the notion of being closed to that of being open. So a set S is closed if the complement of that set is open. Right? So that's what it means for a set to be closed, that it's complement. So again, remember C minus S, this here notation is set minus. So that means C minus S is going to be all the points that belong to the complex plane, but that do not belong to S. Right? So that's, and we say a set is closed if its complement is open. All right, so what we're going to do is we're going to look at the following example here. All right, so what we are going to do is we're going to try to determine if the closed disk, I don't know why I switched into K here, so closed disk is closed or not. All right, so that's the question we're trying to answer here. So a closed disk here, the difference between a closed and open is that it includes its boundary point here. So a closed disk is going to be a set of points centered at A, but it includes the boundary points there. So, and the notation, we're going to put a little bar over the D to indicate that it's closed. All right, so before we ask the question about whether it's closed or not, let's ask the following question. Is this open? Right, so remember, for it to be opened, no matter what point I take, I should be able to find an open disk around that point that is completely contained in the disk. Remember, now this contains the boundary here. So if I was to take a point on the boundary, right, and I considered an open disk, no matter how small or how big I made, how small or how big I made this disk here, it's always going to hit the outside portion here, right? So it's not going to be completely contained. So this is not open. So not being open is not the same as being closed, right? So that's something we're going to have to get used to it. Right? But the question now is that thing closed or not? So let's look at the complement of that disk there. So what happens if we take this disk, DAR, which is right here, and if I remove that from complex plane, what I'm going to be left with is I'm going to be left with a screen there. So this right here is going to be my C minus my set S. Okay, so that's the complement of the closed disk. So the question now is this thing open? And the answer is yes, right? Because no matter where, what point I take, I'm going to be able to find an open set. Even if I take this here, I can take a smaller one, even smaller one. So no matter what point I take in the complement, I can always find an open disk centered around that point that is completely contained in the complement. So C minus DAR is open because for every point in the complement, there is an open disk centered at that point completely contained in the complement. Right, so wonderful thing is a closed disk is closed and an open disk is open. So the final few topological ideas that we're going to introduce are the notion of bounded and compact. Right, so what does it mean for a set to be bounded? A set is bounded means, here's the exact definition, there exists a constant M such that for all Z belonging to the set S here, Z is going to be less than M. Yes, less than or equal to. Doesn't really matter, but I think that's what the book uses, so we're going to stick to less than or equal to. All right, so that means no matter what point I pick in the set here, its modulus is going to be less than or equal to M. So if we think about this in terms of geometry, what that means is if I take any point in the set here, so the modulus Z I can view as Z minus 0, right? 0 being the complex number 0. So what that means here is that if I take any point in that set S, it is going to be contained in a closed disk of a radius M centered at point 0, because everything in that set here has distance less than or equal to M. Right? So in other words, we say a set is bounded. Let's say this set here, if I can find a disk, giant closed disk, so that that set is centered, that set is contained in that disk there, sorry. All right, and next, for compact, we say a set in the complex plane is compact if the set is both closed and bounded. Right, so that's what it means for a set to be compact. All right, so a few examples here of compact sets. And the three examples of compact sets that I want you to keep in mind is, first one are line segments. Right, so if you have line segments, not line, so line segments, and the notation, remember, was alpha, beta in C. So this is not a closed interval, this is a line segment. So again, remember, alpha, beta was defined as T alpha plus 1 minus T beta. Oh, sorry, it was the other way around. It was 1 minus T alpha plus T beta, where T is between 0 and 1. And the idea was when T was 0, we're going to be at alpha. When T is 1, we're going to be at beta, and this is a line. So this is a segment joining alpha and beta. So that's going to be compact because you can show this, that line segments are both closed and bounded. So that's going to be a nice homework question. All right, so the next one are circles. So set of points satisfying z minus alpha is equal to r. Right, so circles are also compact. And finally, closed disks. So those are three examples of compact sets that I want you to keep in mind.